Where did everything come from? We don't know where the universe came from. What's keeping the stars in the galaxy? Most of the matter in the universe is something very, very different.
When we hear dark matter, well, we think of the black hole.
There could be dark matter in the room with you right now. Future is always towards the center of the black hole. Galaxies are holding themselves together, so there's some invisible source of gravity. There might be something else that we haven't understood and imagined.
Do you think there are aliens or alien beings out there?
I would love if aliens came and visited and talked to us. Imagine talking to them and transforming our understanding of the universe by 1 billion years. No matter what answer AI gives us, we're always going to have more curiosity. That's the thing that AI can't replicate.
What if I told you all around us that we cannot see, cannot touch, and still don't fully understand? Scientists call it dark matter, and there could be a dark matter wind passing through this room right now. But that's only the beginning. What is really happening inside a black hole? Could black holes hold the clues to a completely new understanding of physics? Could there actually be other dimensions beyond the 3 we experience? And then comes the question almost everyone wants answered. Are we alone in the universe? What if an alien civilization actually appeared in our solar system? Would you try to communicate with them?
And here's the shocking part. Would you take that risk, even if those beings could potentially be dangerous? Because imagine encountering a civilization that could be millions or even billions of years ahead of humanity. What could they teach us about the universe? And now, just when we thought the biggest mysteries belonged to physics, AI is changing the game. Could artificial intelligence read more scientific research than any human possibly could? Could it connect discoveries that humans never thought to connect? Could AI eventually help us answer questions about the universe that have remained unanswered for centuries? So what happens when dark matter, black holes, aliens, other dimensions, quantum physics, and artificial intelligence all collide in one conversation? Today, we're going there. Because the most frightening thing about the universe may not be what we have discovered. It may be how much we still haven't.
Welcome to Khan Clinics, and I'm your host, Dr. Amir Khan. Today, we're really excited with the guest that we are coming to our show today. We have Professor Daniel Whitson. Dr. Whitson has dedicated his career to helping people ask bigger questions, challenge assumptions, and discover the extraordinary hidden within the ordinary. Professor is one of the world's leading scientists, communicator, and internationally recognized experimental particle physicist. He is based in Irvine, California, USA, and he currently serves as a professor of physics and astronomy at the University of California, where he leads research exploring some of the biggest unanswered questions in modern physics. His scientific work is closely connected with CERN's Atlas experiment, one of the largest scientific collaboration in history. In addition, Professor Whiteson has co-created Cryphus, an innovative smartphone application that transforms everyday mobile phones into cosmic ray detectors, allowing ordinary people to contribute really to scientific research and data. He's the author of internationally acclaimed books, including We Have No Idea, Frequently Asked Questions About the Universe, and Do Aliens Speak Physics? He's also the co-host of Daniel and Kelly's Extraordinary Universe, and he's the co-creator of Eleanor Wonders Why, an animated educational television series shows on PBS Kids to make scientific entertaining, accessible, and very enjoyable. Professor, welcome to Khan Clinics.
Thanks so much for having me here. I'm very excited to talk to you about all the amazing and extraordinary mysteries in our universe.
Now we're excited too. So where do we want to start from? I mean, we're very intrigued by, let's start from the beginning, your childhood. Why go on this path? What intrigued you? And why are you differently seeking out questions and answering, exploring stuff that other people dare to ask?
Well, most people are curious about the universe. I think it's a natural human condition to wonder, why are we here? What are things made out of? Where did everything come from? And I'm basically still asking those questions because I never found satisfactory answers. It amazes me that despite all of our technology and our progress and our understanding of physics and century of success in modern physics, we still do not have answers to those basic questions. We don't know where the universe came from. We don't know how it began. We don't know how big it is. We don't know what its fundamental constituents are, the ingredients that define what it is. So to me, it's hard to move past those questions without getting answers to them. To me, they set the context for our entire existence. So I don't understand why everybody isn't studying these questions. And so I was naturally curious about that. And I grew up in a scientific family. I went to high school in Los Alamos, New Mexico. Both of my parents worked at the national lab there. And in high school, my physics class was taught by a physicist from the lab who would come in the mornings and teach us AP physics. And he seemed to be having a lot of fun. So I decided to try physics. And 30 years later, here I am, still doing it.
Wonderfully explained. Thank you very much. And it explains and gives our audience a lot of insight about why did you start, and your brain, how does it operate? Because it's not only that you look at the universe as a bigger picture, but you also are very interested in looking at exotic new particles, probing properties of the Higgs boson, investigating dynamic and searching for candidate particles that could explain dark matter.
Yeah.
And for our audience, explain what that means. Because when we hear dark matter, well, we think of the black hole, we think of negative energy that is out there in the universe. But you're looking at it from a completely different angle, obviously bringing in the scientific insight to it. But all the experiments that's done at the Atlas experiment, tell our audience, what does that mean? Why are you looking at these different, rare, extraordinary, high energy particles?
Yes. So, a deep question is, what's the universe made out of? And we have learned a lot in the last few hundred years. We know that everything that we're made out of is made out of about 100 elements, which you can put together. And it's sort of incredible that our universe works that way, that the amazing complexity, blueberries and ice cream and lava and cats and people and stars are all made out of a small number of building blocks. Already, there's insight there. It tells you that complexity in our universe comes from the arrangement of simplicity at a lower level. Like a small number of building blocks can be rearranged to make lots of different things. It's like the Lego principle, how you can make anything out of Legos, out of a few basic building blocks. And we've drilled down and understood that to some extent, though there's a lot of open questions. But then we realized about 50-ish years ago that the matter we've been studying, the stuff that makes up me and you and our children and our lunch, isn't the most normal matter in the universe. In fact, it's a very unusual kind of matter. And most of the matter in the universe is something very, very different. And we didn't even know that it existed until recently because it doesn't interact the same way that normal matter does. Normal matter, for example, gives off light or reflects light so you can see it. The reason you see an apple in front of you is because the sun hits it with its rays, and then the apple absorbs some of those and reflects some of those, and those light rays go to your eye and you see it. But if there's matter out there that light passes right through, and it doesn't reflect and it doesn't emit any light, you can't see it. But we can detect that it exists because all matter has one fundamental property, is that it generates gravity. Like the reason that the earth is going around the sun and the reason that you're stuck to the earth is because of the gravity of those massive objects. So invisible matter that's out there, you can detect it through its gravity. So essentially, dark matter is a way to explain a lot of unexplained gravity we've noticed over the last 50 years. Like when we look at how galaxies rotate, you can ask, well, what's keeping the stars in the galaxy? If I put a bunch of ping pong balls on a merry-go-round and I spin it, the ping pong balls fly out. If a galaxy is spinning, why aren't the stars flying out? Well, the answer is gravity is holding it together. But if you add up all the gravity from all the stars, there isn't enough gravity there from all the visible luminous matter to hold the galaxy together. You need much more gravity than we can account for to keep the galaxy from throwing stars into intergalactic space. And yet galaxies are holding themselves together. So there's some invisible source of gravity that's holding the galaxy together. It's a big idea. And scientists were skeptical for decades until we saw many other independent lines of evidence for this kind of matter. We see how it affected the early universe. We see how it affects the overall structure of the universe. For example, without dark matter in the universe, we wouldn't even have galaxies. So we know that it's there, but you asked about, why are we doing experiments for this at a particle physics collider? And the answer is that we want to know, what's it made out of? Like, we can tell that it's there. There's a lot of it. We can tell roughly where it is, but we don't know what is it. Like, is it made out of a particle? Is it made out of something totally different? Is it 17 kinds of particles? We don't know. And one way to figure that out is to look for how dark matter acts as a particle. Does it act as a particle? Can we see it bouncing into stuff? So most of the research right now is trying to identify the particle nature of dark matter.
So, Professor, you've explained it brilliantly. I think, and if we analyze a little bit more, and for my audience a little bit, just to clarify, the universe is dark matter. It's made 25, 30, or 40% of this matter that we don't really understand what it is. The only thing we know, it does not reflect light, it doesn't absorb light, it doesn't emit light. And we know that it's related to gravity somehow, and it's connecting our universe together. So it's dark, it's what is it right to say it's invisible as well?
I think invisible is a better description than dark. Dark is the official name, but that suggests that if you had a bunch of it around you, it would block your view. And that's how they show it in science fiction all the time. But actually, it's invisible matter. So there could be dark matter in the room with you right now.
Interesting. And the particles that you are studying may be in the so-called invisible matter or the dark matter. And they are on Earth as well. They're with us.
So. Yeah. We don't know very well where dark matter is because we can only sense it gravitationally. And gravity is much weaker than any of the other forces. So in order to sense dark matter, you need a lot of it. So we can tell where dark matter is by its gravity only when there's really big blobs of it, like Jupiter-sized blobs. So we think dark matter is here and it's sort of spread out evenly through the solar system. There's more dark matter in the universe than there is normal matter, but dark matter is less clumped up. It's more spread out.
So that's brilliant. We've got particles. These particles, you've described the character. We've got this matter that exists out there, this in the universe that we're still exploring. We're looking at it and trying to net that together with the gravity. The universe is expanding. Mm-hmm. And then in the midst of it, there are these gigantic black holes that exist.
Yes.
How much do we really know about these? We know a little bit about the gate. Do we know anything more than this? Or is it all to be studied, science fiction. As a physicist, I would love to hear your answer. Say,
Yeah.
where are we with exploring this more? Are these really gateways? How would you explain it to our audience?
Yeah, it's a great question. So black holes are funny because there's something that were predicted by physics 100 years ago, but physicists for a long time were sure that they didn't exist. It seemed like sort of an oddity. People thought, well, that's weird. I'm sure something would prevent that from happening. The math seems really strange. And a black hole is a place in the universe where there's so much mass that space itself gets curved so that space is now just one directional. You know how like time is one directional. You can only move forwards in time towards the future. Inside a black hole, space is also one directional. So the future is always towards the center of the black hole. And so no matter which way you go, there is only one way to go, and that's towards the center. And so this seemed like a fantastical prediction until we saw something like it. We see things out there in the universe that are extraordinarily small and very, very massive. They have a very, very powerful gravity. There's one at the center of our galaxy, and we see things zooming by it. And when they zoom by it, they turn really fast, which can only happen if there's a very strong force. And so we deduce that these are black holes because there's nothing else in our theories that is so massive, so compact, and so dark. And so that's the evidence for black holes. But a black hole is dark. What we actually took a picture of was gas surrounding the black hole. If you look at the picture, it's like a glowing donut. That's the hot gas surrounding the potential black hole. So it might be a black hole, but it might be something else that we haven't understood and imagined. And nobody has been able to unify these two theories into a theory, we call it quantum gravity, to explain what might happen in that situation. What are we actually looking at out there in the universe? What is inside a black hole? And because space is one directional inside a black hole, nothing can escape it. And so there's no information from beyond the event horizon that can reach us. So we're in the dark. Within a black hole is likely the answer, the clues, the evidence we would need to come up with a theory of quantum gravity. It tells us what happens in these extreme circumstances. And yet it's hidden from us. We can't see it. So we don't know what a black hole is really. It's probably some quantum gravity object we don't yet have a theory to describe. It's possible there are also these conceptual ideas of white holes, which are the opposite of black holes. A black hole is a region of space things enter but can never escape. A white hole is a much more theoretical object. It's a region of space that you can escape, but nothing can enter. And the idea is maybe a black hole and a white hole are connected by a wormhole, an overlap in space-time, so that you might fall into a black hole, and if you could mysteriously and magically survive the crushing gravitational tidal forces, go through the wormhole and end up being shot out the white hole. That's very theoretical. Nobody knows. It's one speculation. But nobody even has a working theory of quantum gravity that could answer these questions yet. So there's a lot of work to be done, both on the theoretical side and on the experimental side.
Fascinating. It's really fascinating. I have a sort of like a personalish question.
Ooh.
Einstein saw something about 100 years ago.
Mm-hmm.
It's about 100, it's give and take. He's on planet Earth, and he's discussing these gravitational pulls of the universe, not of planet Earth. And he's sort of like, it seems like he's looking into the future. And here we have Professor Whiteson, who first does a bachelor's in physics, and then decides to do a computer science qualification as well, in physics and computer science, which is a rare combination, physics and computer science, in 1997, and then do a PhD in physics.
Mm-hmm.
Isn't that where we're headed right now? That combination, computer science, all this AI learning, all of this massive exploration of the universe. you must be looking at something. It's a strange, odd passion, and considering it's over 30 years ago, Daniel.
Well, that's true. I was doing AI well before it was cool. I was always fascinated with artificial intelligence and computational problems. And so when I went to school, I wanted to do physics because the big questions were exciting, but I also wanted to do computer science because the day-to-day work was fun. I liked writing programs. I liked thinking about AI. I liked talking about what it could possibly do in the future. And I saw an obvious connection there that computational tools would be important for solving physics problems. And, physics is a wonderful field because it's got lots of different kinds in it. You got the people who like to build equipment and climb around with a screwdriver and get greasy. You got the people who like to analyze data and think about statistical questions. You have people who like to write software. And the joy of working in a massive collaboration like I do at CERN is that you need all those kinds of people, and everybody gets to do the part they think is most fun. So I like writing computer programs and analyzing data and using AI. So I've been doing that not because I foresaw the rise of AI in 2020, but just because I thought it was fun. And it just so happens that the world ended up moving in that direction. Everything became more computational, and AI became more and more central to how we analyze our data and how we do our theories and how we think about the universe. So I think I was more lucky than smart. It just happened that the things I was excited to do ended up being things that were useful.
Okay, well, that's fascinating. I'm going to put it in the bracket of being smart or something, or have an intuition. But here's the $1 million question then, following that. Do you think there are aliens or alien beings out there now? As a scientist who is deeply analytic, studying the universe, and then as well being on planet Earth, everyone's asking the same question. You're in a group of your CERN university, your CERN alliance, you're part of European thought processes. So you're listening a lot of, you get a lot of information. What's your thoughts on this?
Yeah, great question. Number one, I would love for there to be aliens. Not just out there in the universe, but here on Earth. I would love if aliens came and visited and talked to us, because, the universe they could be dangerous, absolutely. But, look, the universe is very old, which means alien civilization could be very old. There could be civilizations out there that have been thinking about the universe and exploring it for 1 billion years. What are their thoughts about the universe? What are their questions? Quantum gravity is kindergarten stuff for them. Imagine talking to them and transforming our understanding of the universe by 1 billion years. It's hard to even reckon. And so I want it to happen. And yes, it's potentially dangerous, but, why would an alien species, I can't imagine what an alien species would want with us, because any resources that they need, water, gold, platinum, iron, whatever, it is plentiful out there in the universe. They don't need it from Earth. So, of course, it's always dangerous to project human theories and politics onto aliens. But I hope that when the aliens come, they'll be friendly. And so, because I hope that it happens, and I'm deeply personally invested in it happening, that means that I have to be extra skeptical, because it's very easy to fool yourself to believe the things you want to believe, right? It's easier to accept arguments. You're not as critical of them. So I try to make an extra effort to be skeptical of these things because I know that I'm biased towards them. So I don't think that aliens are likely to be here on Earth with us right now, which is too bad, because I would love for them to be. And I would love for them to be like hard physical evidence that they were here. Bring it on.
So what I gather from this is that there is a believer, Daniel, that wants to believe that there is.
Yeah.
But the professor part of it, Daniel, wants to say, well, the evidence doesn't suggest that right now. And as a scientist, as a theorist, as a physicist, I have to be on the side of caution and say, right now, I can't see it. Would that be a fair sort of answer? So you're not. So if that's a fair answer,
except I'm not in favor of caution when it comes to communicating with aliens. Like if aliens are flying through the solar system and we have to make a decision to say like, hey, come visit, or try to stay quiet so they fly by, I'm all in favor of pressing that red button and inviting them down here, even if there's a chance that they nuke us from orbit, because the information they carry is so incredibly tempting and valuable that I'd be willing to roll the dice to invite them over, which is why I'm not running for public office and I probably shouldn't be in charge of making these decisions. But how could you let aliens fly by with the secrets of the universe and not even ask?
But that's the Daniel the Explorer. That's why you're getting those answers and trying to look for what is going on in the universe and the world. So that leads us to the next question, which has been pretty popular among people who wanted to know about things, is that ask Professor, what does he think about dimensions? And does he think they exist? Is there another dimension of me, you, the Earth, universe? And could it be that those beings are in other dimensions? That's a great
question. The word dimensions has a lot of different meanings for a lot of different people. I think for most people who read science fiction or fantasy, dimensions is like parallel universes or, another reality. And there are ways that our physics lines up with that. For example, there are questions about how things happen in the universe. When an electron could go left or it could go right, and there's a probability for both, how does it pick? And there's one theory, it's called the many worlds interpretation, that suggests it doesn't pick, that the universe splits and both of those things happen. There's one where the electron went left, another one the electron went right. And now those two universes, they both exist and they're in some sense overlapping, but they don't interact with each other. And this is happening constantly, over and over again, millions and millions of universes constantly being spawned. So this metaverse of universes where, you had a coffee instead of an orange juice in the morning, or you were a man instead of a woman, or a different person was president. All these things exist out there in the universe as potentially other dimensions. The issue is that in that theory of physics, there's no way to interact with those other dimensions, those other versions of the universe. In science fiction, they're always, jumping from one to the other, etc. You have hot dogs in your fingers in one and real fingers in another. But physics says you can't do that. There's no way to go from one to the other. But when we talk about dimensions in physics, we usually mean something different. We mean directions of motion. So in our universe, we think about having 3 directions of motion. Like I can move forward, backwards, that's 1, up and down, that's 2, left and right, that's 3. And that describes everything, right? We have 3-dimensional space. But the question is, well, why 3? Like 3 is a weird number. The Catholics like the number 3, but why does the universe like the number 3? And so maybe there are more, because if there were more dimensions to the universe, then we would be essentially like living on a 3-dimensional sheet of a higher dimensional universe. That's hard to think about unless you think in lower dimensions. So imagine that we are creatures living on a 2-dimensional plane in a 3-dimensional space. We're living on like one sheet of a book, one page of a book, and there are other pages there with maybe other creatures living on. And those creatures maybe live in the full space and they can move through our space, in which case we would see them appearing and disappearing. So if we live in a little slice of the universe, then we're not seeing everything. And there definitely could be beings and creatures and even particles and massive objects, which might explain dark matter, in those other dimensions and not in ours. But remember that gravity tells us about all the matter in the universe. So if there is other stuff out there, we would be feeling its gravity. And very importantly, gravity would behave differently. Because the way that gravity gets weaker with distance,
if they're saying you could be at one place and I'm going to pull the gravity in such a way and you could actually end up being in another dimension, another place, physics-wise, because we're just adjusting how we're making the loop. So that's scary. That's really mind-blowing to us.
Yeah.
So please, so the future.
Yes, the future. What does it hold? Anthropic tells us they're going to solve physics. And I say, I don't know what that means. You know, yes, we have questions about physics right now that we'd love answers to. But even if we got those answers, physics would not be finished. It's not like we'd be like, oh, okay, I'm done. I have no more curiosity. Physics is inherently a human endeavor by curious creatures who want to understand their environment. And no matter what answer AI gives us, we're always going to have more curiosity. We're always going to be interested. If AI comes up with some theory of everything and solves quantum gravity, we're going to ask, well, why is it that theory? You know, it's some other theory or something else. And so, you know, we're never going to be done asking questions. But let me also be excited about the future of AI. Let's think about what it's actually capable of doing. I don't think it's capable of replacing human curiosity. We're always going to be the ones asking the questions. But I do think it's capable of giving answers. You know, what can AI do? It can read every paper. I can't do that. There's just so many papers being written right now that I can't, even if I spend hours every day reading, I can't keep up. But I don't think we're going to not work, that we're going to not ask, that we're not going to be interested. I think that's, you know, a little bit too much hype.
Interesting. So you think if I tell my kids to go into a field, you would say today what? Not sure if they should go into medicine. Not sure if they're being engineers now. Not sure whether computer science, probably I would still push that, but considering there's a big number of people out there that have not pushed themselves, I'd say.
Well, I would say follow your curiosity. You know, that's the thing that AI can't replicate. If you're curious about, you know, how the human body works, go pull on that thread. If you're curious about the universe, go pull on that. If you're curious about how organic molecules come together, follow that, because it's human curiosity that drives all of these things. And that can't be replaced. Even though the tools are going to transform the way the work happens, the reason for the work is not going to change.
Brilliant answer. It is brilliant answer, because at the end of the day, you've got to be passionate about it. And unfortunately, there's not a lot of people like you, because they're passionate about what they do, and it's hard. Final message for our audience, Professor.
Yeah, follow your curiosity. You know, stay excited. Listen to what's in your heart about what you love and what you're not enjoying doing, and do the fun bits, because that's the places where you'll shine.
Brilliant. Professor, it's a pleasure having you today on our show today.
Thank you very much. Really fun to talk to you.
Same here. And to our audience, if there is any part of this that elicited your curiosity and answered your questions, or maybe even opened more questions and answering some of them, do remember to share, click subscribe, Khan Clinics, and the bell icon. Don't remember to press that as well. Share this podcast with someone who loves asking questions, who wants to explore. And to explore means to go out and find new discoveries. That's not going to stop. From Khan Clinics, have a wonderful evening.